Hello viewers. So today in this video I am going to cover 3.6 complex zeros and the fundamental theorem of algebra. Okay, so in the last video we covered 3.5, which talked about complex numbers. So now we're going to take a look at again, higher degree polynomials. We're coming back to higher degree polynomials, and we're going to be looking at all of the zeros. Okay, so complex zeros. And this is going to be a long part. Fundamental theorem of algebra. Okay, so let's start off with the fundamental theorem. We're going to look at a couple of theorems here before we look at factoring completely. Okay, so fundamental theorem of algebra. Let me just do this, because we do have one for calculus as well. Okay, so every polynomial p of x, which is some degree n, whatever that is, some nth degree polynomial. And of course, this is for n greater than or equal to 1 and a n not 0. That's just for simplicity's sake. Okay, just some details here. So every polynomial p of x with complex coefficients has at least one complex zero. Okay. And then we're going to also look at the complete factorization theorem. Okay, so here, this one states that if p of x is a polynomial of degree n, it's going to be greater than or equal to 1, then there exists complex numbers A and C1, C2, C3, Cn with A not 0, can be any other number, such that the polynomial p of x can be written as a times x minus c1, x minus c2, x minus c3, etc. Okay, so what this is saying is that your whatever degree your polynomial is, then you could factor it into n linear factors. Okay, so that'll probably make more sense when we look at an example. Okay, so let's take a look at factoring completely. Okay, so when we're factoring completely, so it may not look or it may not be factorable right off the bat. But we looked at how to find the zeros of higher degree polynomials when it's not factorable, and we looked at how to use synthetic division to find these zeros. Okay, so if it's not factorable right from the get-go, then find all the zeros using your synthetic division process. So you're going to find all the zeros, and you're going to, once you have all your zeros, then you can derive the factors by essentially working backwards from what you used to do. So derive the factors from the zeros. Okay, so for example, if I have to factor completely, p of x, which equals x cubed minus 3x squared plus x minus 3. So if I want to factor this completely, then that means that I have to come up with my linear factors, like this one here is saying that you can come up with your linear factors. Okay, so let's take a look at this. Okay, so you might be looking at this polynomial and saying, oh, well, it's factorable. I can factor that by grouping, and that is true. Okay, so hopefully you looked at this polynomial and you said, oh, okay, well, I can group these two together and do greatest common factor here. Between these two, I can factor out x squared, and I would be left with x minus 3. So this is factoring by grouping. I group the first two terms together and I factor out the common factor. I take the next two here and I factor out their common factor. Well, it's only going to be 1. So I'm going to factor out 1. Okay. And then this is one term and this is one term, separated by addition there. And we see that both of these here have x minus 3 in common. So I'm going to factor out the x minus 3. And what I'll have left here is x squared plus 1. Okay, so normally in the past, you guys would stop here and you would say, okay, well, x squared plus 1 is not factorable. And you would box your answer and be done. Okay, so what we're doing here is we're saying, okay, well, yeah, you were told in the past that maybe this isn't factorable, okay, which is only partially true. It's not factorable over the real numbers, meaning that you can't factor this using just real numbers. However, you can factor it using complex numbers, okay? So, so let's go ahead and let's find all the zeros, okay? So x minus 3 equals 0. So add 3 to both sides, and x equals 3. Okay, there's 1, 0. Okay. X squared plus 1 equals 0. Subtract 1 on both sides. Take the square root of both sides. And hopefully you all know that the square root of negative 1 is I. Okay, so here are your other two answers. X equals I, x equals to negative 5. So we have these 3 zeros. Okay. So I had written at the top, you're going to go ahead and find all the zeros. And then from that, you should be able to derive your factors from your zeros. Okay, so we have x equals 3, x equals I, and x equals negative I. So we can derive the factors by just bringing that zero, that solution, back over with the x. So here I would just subtract 3 on both sides, right? So I get x minus 3, and that's one of my factors. I'm going to subtract I on both sides. So I get x minus I is another factor. And this one here, I'm going to go ahead and add I to both sides. And so my third factor is x plus I. So when they say factor completely, they want you to factor it into linear factors. Okay. So that's what this is saying, this theorem right above here, up here. They said this complete factorization theorem, it says if p of x is a polynomial of degree n, so we had degree 3, then there exist complex numbers such that your polynomial can be factored into linear factors. Okay, so you don't see here, you don't see any x squares. Okay, but those c's represent complex numbers, and that's what we have here. So right in here, that c value is I, and then this one is negative I. Okay. All right, so when they ask you to factor completely, come up with the zeros first, and then derive the factors from your zeros. Okay, so let's take a look at one. This one was nice because at least here, it initially it was factorable, so not too challenging here. Okay, so let's go ahead and take a look at this example where it's not factorable and we have to do that longer process of where we use the synthetic division. Factor completely. And suppose that I have x cubed minus 2x plus 4. Okay, so clearly that is not factorable. So I'm going to use my synthetic division, rational zeros. Okay, so plus minus 1, plus minus 2, plus minus 4, all the factors of 4. And then over here, all my q values, plus minus 1. Okay, so my possible zeros are going to be all the positives and all the negatives of 1 over 1, which is 1, 2 over 1, which is 2, and 4 over 1, which is 4. Okay. Okay, so I always like to start off with 1. Okay, so the coefficients of the polynomial, I'm going to have 1. X squared is missing, so I'll put a 0. And then negative 2 and 4. Okay, bring down the 1, multiply. 1 times 1 is 1. Okay, combine. 0 plus 1 is 1. And repeat the process. 1 times 1 is 1. Combine negative 2 and positive 1, and that'll give me negative 1. Multiply. Negative 1 times 1 is negative 1. 4 minus 1 is 3. So we didn't quite get a 0 here. Okay. Anyone feeling lucky? Any viewers feeling lucky? Do you think you know which one it will be? Okay, so just go ahead and say it to the screen, and I'll hear you. All right, I hear you guys. I hear you guys saying negative 2. Try negative 2. All right, let's try negative 2. 1, 0, negative 2, 4. Okay, bring down the 1. 1 times negative 2 is negative 2. And then we're going to combine 0, negative 2 is negative 2. Repeat the process. Negative 2 times negative 2 is 4. Combine 4 and negative 2 is 2. 2 times negative 2 is negative 4. And oh, look at that. Oh my goodness, we got a 0. All right, so not just any 0, but a happy 0. Okay. All right, so we found one of our zeros. This was the original problem was degree 3. Okay, so then that would make this one here a degree 2. Okay, so this would be a degree 2 polynomial. So this is x squared minus 2x plus 2. Okay, so let's see if this factors x times x. Both of these negative, 2 and 1. That doesn't work. So unfortunately, this is not factorable. Okay, so we're going to go ahead and use the quadratic formula to solve that quadratic. So x squared minus 2x plus 2. So a equals 1, b equals negative 2, and c equals 2. So x equals negative b plus or minus the square root b squared minus 4ac all over 2a. All right. Scroll. So we get 2 plus or minus the square root of 4 minus 8 all over 2. And this will give me 2 plus or minus square root of negative 4 over 2. And square root of negative 4 is going to be 2i. Okay, I'm going to go ahead and factor out a 2 in the numerator. And so now I can cancel this out. Okay, so then my answers, my zeros, are going to be this one up here, x equals negative 2. And then from over here, I'm going to get x equals 2 plus I. And x equals 2 minus I. Okay, so then my factors, I can go ahead and derive them from the zeros by working backwards. So here in this first one, I'm going to go ahead and add 2. So my first factor is x plus 2. And over here, I'm going to subtract 2 and subtract I. So I'm going to subtract 2 and subtract I here. So I get x minus 2 minus I. And over here, I'm going to subtract 2, add I, and add I. Okay, so my third one is going to be x minus 2 plus I. So here we see that these are all linear factors, meaning that you don't see an x squared. Okay, so we have factored completely. Okay. All right, so a bit of a note on zeros and their multiplicities. Okay, so it turns out that every polynomial of degree n, and of course this n is greater than or equal to 1. So every polynomial of degree n has exactly n zeros. So if it's a degree 3, it'll have 3 zeros. If it's degree 5, it'll have 5 zeros. If it's degree 4, it'll have 4 zeros, etc. Okay, has exactly n zeros. And then also zeros of multiplicity k will be counted. K times. Okay, so for example, if you have a polynomial, a degree 10 polynomial, and suppose your degree 10 polynomial factors out to this: x minus 1 cubed, x plus 2 squared, x plus 3 to the 5th. Okay, so your degree 10 polynomial has exactly 10 zeros, right? Okay, so, well, the zeros would be x equals 1, right? X equals 1, x equals 1, x equals 1. Okay, because it's multiplicity 3. And x equals negative 2 is also 0. And it has multiplicity 2. Okay, and then x equals negative 3 is 0 with multiplicity 5. So here, this is a degree 10 polynomial. Like if you multiply it all out, you'll get x to the 10th power. Okay, and so since it's a degree 10 polynomial, it should have 10 zeros. Well, this is a factored form, but they have multiplicities 3, 2, and 5. And so we see that we get all 10 zeros if we write all of them out. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros listed. Okay. All right. And that's this theorem is good for you guys when you're factoring and trying to solve. It's a good way to check to see that all of your answers make sense. Okay. A note about conjugate zeros. We have a theorem here. And this one's also a good one to know. Okay. So if polynomial P has real coefficients and complex number a plus bi is a 0. Okay, so if you have a polynomial with real coefficients and it turns out that one of the zeros is a plus bi, like maybe it's 3 plus 2i, then its conjugate, a minus bi, is also a 0. Okay. So this is going to be useful when you're given a list of zeros and asked to find the original polynomial. Okay, so if they only list one of these, a plus bi or a minus bi, and oftentimes they will, you have to just be able to look at them and go, oh, well, a plus bi is a 0, so I know a minus bi is, and you need to make sure you include it on your list. Okay. All right, so let's try an example here. Find a polynomial with integer coefficients that satisfies the given conditions. Okay, so suppose that they give you the following information. It has a 0, x equals 1 plus I square root 2. Okay. Okay, so if this is all the information they give you, then over here, because that's a complex 0, then we know that x equals 1 minus I square root 2 is also a 0. Okay, so you need to include it on your list when they're giving you a list of zeros. If they only give you one of the complex zeros, make sure you have its conjugate listed. All right, so now we need the factors. So for this first one right over here, so I'm going to subtract 1 on both sides, right? I'm going to subtract 1 on both sides, and I'm also going to subtract I square root 2. Okay, so my first factor is going to be x minus 1 minus I square root 2. And over here, the other one that I know, I'm going to subtract 1 both sides, and I'm going to add I square root 2. Okay, so then my second factor is going to be x minus 1 plus I square root 2. Okay, so then here, I'm going to go ahead and multiply this out. Okay, so you can go ahead and distribute. X times x is x squared, and then x times negative 1 is negative x, and then plus xi square root 2. Okay, now I'm going to go ahead and distribute the negative 1 to all of those terms in there. So I'm going to get negative x, I'm going to get positive 1, and I'm going to get negative I square root 2. And now I'm going to distribute this last term to all of these guys over here. So I'm going to start on a new line here. I'm running out of space. Actually, let's see. Yeah, okay. All right, so I'm going to get negative xi square root 2. And then I'll get positive I square root 2. And then I'll get negative I squared and square root 4. Okay. So let's see if anything cancels out here. They do. So this one over here cancels out with this one over here. Okay. This one over here cancels out with this one over here. And we know square root 4 is 2. So this here is really negative 2i. Okay. All right. So did I forget my square? I did forget my square. Negative 2i squared, right? Okay. I'm waiting for it to show up. There it is. Okay. It's starting to slow down here. And then we know that I squared is negative 1, so that'll change that into a positive 2, that last term. Okay, so what happens is when you multiply these all out, even though you have all these radicals and imaginary numbers, what happens is they should all cancel out or disappear somehow. And so you should end up with just real coefficients. So we have an x squared there, and then a negative 2x, because I'm combining that one and this one. Okay, and then I get plus 3. Okay, plus 3 because it's this one right over here and this one over here. Okay, so here's my polynomial, real coefficients. Like I said, when you multiply these out, you should get a polynomial with just real coefficients. Like I said, your radicals should cancel out and your imaginary numbers should also cancel out. Okay, let's do this one. Find a polynomial. P that has degree 3 and the following zeros. 2 minus I and 1. Okay, so let's see. What do we know? We know the zeros. So we know x equals 1, and we know x equals 2 minus I, but that's a complex zero, so we are brilliant. And so we know, oops, so we know that x equals 2 plus I is also a 0. Okay? All right, so hopefully you know that. Because remember, they always come in conjugate pairs. Complex zeros come in conjugate pairs. Okay, so let's come up with our factors. So whenever they're asking you to find a polynomial starting with the zeros, you list your zeros, then you get your factors, and then you multiply them out. All right, so this first one, so x equals 1, so I'm going to subtract 1 on both sides. So my first factor is x minus 1. My next factor, I'm going to subtract 2 on both sides and add I on both sides. Okay, so my second factor will be x minus 2 plus I. And then my third factor, I'm going to subtract 2 both sides and subtract I both sides. So I get x minus 2 minus I. So there's another way you can look at multiplying. I would definitely do these two first, multiply these two out together. You can go one term at a time like we did in the previous example. That's fine. I'm going to show you another way to do this. Okay, so suppose that I have this. Let's see. All right, so I'm going to rewrite these two factors in a different way so that hopefully you can see what I mean. Okay, so I'm going to have this x, okay, and I'm going to have this. I'm going to factor out a negative from these two. Okay, and that'll give me what I have here, right? Okay, and then over here, I'm going to factor out a negative as well. So that'll be 2 plus I. Okay, so you have this here. So what you can do is multiply them individually like this. Okay, so instead of looking at this as two different ones, yeah, two different ones, you can look at it as a single entity and then multiply that out. Okay, so that's just another way to look at it, but it doesn't matter how you do it. If you want to do one by one, I would recommend multiplying these two together first. Okay. All right, so let's go ahead and do one by one. So x times x is x squared, and then minus 2x minus ix. And then distribute this negative 2 to the three terms over there. So we get negative 2x plus 4 plus 2i. And distributing the I to those three terms, and I get plus xi minus 2i, and then minus I squared. And again, things should cancel out. So let's see. Uh-oh. Where did we go wrong here? Nowhere. So these two cancel out. Ix, 2i, and negative 2i. So again, the i's should cancel out. And then we already know that I squared is negative 1. So this here will become positive 1. Okay. Trying to get this to scroll. Okay, so then what I need to multiply next is x squared minus 4x plus 5. Okay, that's when we combine like terms. I have x squared right there, and then I combine my negative 2x and negative 2x right here and right here. And then I combine my constants, positive 4 and positive 1, right here and here. Okay, so let's finish multiplying this out so that we get the final polynomial. So we get x cubed minus 4x squared plus 5x minus x squared plus 4x minus 5. Okay, so I distributed the x, and then I distributed the negative 1. And so my final polynomial, combining like terms and putting it in descending order, I get x cubed. So that's that one. Negative 5x squared. Okay, so that's this one and this one. And plus 4x. Okay, so you might want to double check that. Okay, so there's a lot of multiplying there, lots of room for error. But if you redo that problem, you're like, Ms. Cortez, I don't think that was exactly the right part over here. If you notice something, usually we're doing this together in class and someone points out like a mistake while I'm in the process. But it's hot right now. I don't have AC, and I'm going to make all the excuses in the world. Okay, but anyway, so that's it. So that's it as far as finding polynomials. Just make sure that you start with finding the zeros, then get the factors, and then multiply. Okay. And yeah, lots of room for error. Look at this mess. Okay. All right. All right, you guys, if you have any questions, if you want me to redo this problem, I can. Unfortunately, my recording thing doesn't allow me to pause and edit and whatnot, so I have the really cheap version here. Okay, so email me if you have questions or if you need me to have a Zoom meeting with you. All right, have a good day.